status improvement as the incorporated higher education with A accreditation. This achievement is in line with the commitment of all policymakers. The nation's competitiveness through a quality learning process and innovative research. The representative learning facilities and strategic campus in the center of Bandung City, Bandung Regency, and higher education zone in Jatinangor, Sumedang make UNPAD as an excellent university in conducting education, research, and community services. Through its best programs enabling to fulfill the needs of society. Nowadays, UNPAD has 16 faculties and 1 postgraduate school, totally consisting of 152 study programs. Faculty of Law, Faculty of Economics and Business, Faculty of Medicine, Faculty of Mathematics and Natural Science, Faculty of Agriculture, Faculty of Dentistry, Faculty of Social and Political Sciences, Faculty of Arts, Faculty of Psychology, Faculty of Animal Husbandry, Faculty of Communication, Faculty of Nursing, Faculty of Fishery and Marine, Faculty of Agricultural Industry Engineering, Faculty of Pharmacy, Faculty of Geological Engineering, Postgraduate School. Realizing the importance of learning process, curriculum and learning method are continuously developed in order to adjust the dynamics of stakeholders' needs. Nowadays, UNPAD has used student-centered learning method. That is, learning method focuses on students as the base to actively involve in developing knowledge, skills, attitude and behavior with competence-based curriculum. Supported with professional faculty members and staffs, UNPAD is capable of generating competitive and characterizing graduates. Until now, it has registered 10,000 of students from all over Indonesia and hundreds of international students studying in Universitas Pajajaran. To optimize the education and learning processes, UNPAD is supported with various representative supporting facilities such as library, Basic Science Service Center, Language Center, e-learning, Teaching Hospital, and Dental Hospital. In addition, UNPAD is also equipped with student dormitory, health facility, sport facility, campus transportation, banking, hall, and entrepreneurship facility. Such various facilities are supported with the utilizing of information technology. Besides supporting the academics quality, Universitas Pajajaran also fully supports the activity of student character building through some student unit. As a part of society, Universitas Pajajaran absolutely realizes that its function is limited not only in teaching, but also social and cultural aspects. Some social activities, society empowering, and research implementation have been conducted to give real benefits for all society. Universitas Pajajaran, straightening and developing together with society. From West Java, for Indonesia, to the world through SDGs.
Good morning, good afternoon, and good evening, dear colleagues and fellow students. It is nice to see you all again in the second session of the webinar, Introduction to Statistics for Health Research, held by Dental Faculty, Universitas Pajajaran. And first of all, I would like to thank our Dean, Dr. Nina Justiana Ardana, our Head of International Affairs, Dr. Eris Karyanti, and of course our helpful colleagues, International Office Associate, Dr. Erli Sarlita, for facilitating this webinar. And now I'm welcoming Dr. Nina Justiana to deliver opening remarks. Dr. Nina Justiana, the floor is yours.
Thank you very much, Dr. Amalia. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore dan salam sejahtera untuk kita semua. A very good afternoon to you all. It is my great pleasure to address at the opening of today's seminar on Introduction to Statistics for Health Research, Part 2, which is the Part 1 already held last month. On behalf of the Faculty of Dentistry, Universitas Padjadjaran, I would like to express my gratitude to Dr. Marisa Hijriana from Edinburgh Dental Institute, the University of Edinburgh, United Kingdom, for sharing her time and knowledge with us today. I personally met Dr. Marisa in Edinburgh last February, actually, just before the pandemic, when we were having a meeting on bilateral collaboration with Edinburgh Dental Institute. In this unfortunate circumstance, where we have to stay at home, all of us, but we have to keep up our productivity. Here today, undergrad and postgraduate students, lecturers, researchers, and dentists from Indonesia and all over the world have gathered to learn about statistics in health research from the expert. Once again, thank you, Dr. Marisa, for your time. Hopefully, this is the beginning of many academic collaboration in the future between our institution. Ladies and gentlemen, please enjoy this webinar. Thank you very much.
Thank you, Dr. Nina, for this welcoming session. And now we proceed to Dr. Eriska. Please, Dr. Eriska, maybe we have a few words to welcome the audience. Dr. Eriska, the floor is yours.
Welcome to Universitas Padjadjaran webinar series. My name is Dr. Eriska Rianti. I am the head of International Unit, Faculty of Dentistry, Universitas Padjadjaran in Indonesia. Today's webinar is the one among several series of international collaboration webinars, presenting world-class speakers. And today, we are very happy to host over 500 participants from Indonesia and other countries, including India, Canada, Netherlands, and United Kingdom, comprised of not only undergraduate and postgraduate students, but also lecturers and researchers. We are looking forward to meet you again at our next webinars. Please follow the links on the YouTube video description. Stay safe and keep learning.
Thank you very much, Dr. Eriska. Before we start the presentation, I would like to introduce our speaker today, Dr. Marisa Hidriana. She was the alumni of Universitas Padjadjaran from dental faculty, and she was studying dental science from 2003 to 2007 with great distinction, and then proceeding to Doctor of Dental Surgery in 2007, 2009, and then she undertook Master in Public Health Methodology in University Libre de Bruxelles, Belgium, from 2012 and until 2013. And now she is in PhD program in the University of Edinburgh, UK. Okay, so without further ado, please welcome our speaker, Dr. Marisa Hidriana.
Thank you, Dr. Amalia. Thank you so much for the opportunity. Good morning from the UK and good afternoon for you in Indonesia. And I hope the time is quite comfortable for others in different countries. I would like to say thank you to the Faculty of Dentistry, University of Padjadjaran for the opportunity. And I'm happy to be here for our second part of the webinar about Introduction to Statistics in Health Research. And if some of you did not attend the first part of the webinar, don't worry, because I will do a quick review about some key points from the part 1 of the webinar. And in this webinar, we will not go further in with the mathematical properties of the statistic, rather than focusing ourselves in understanding some of basic concept and the application of the statistic tests. And as per usual, before we go through the contents, I would like to check if you have seen my first page of my PowerPoint right now. Could you please confirm this, Dr. Amalia?
Yes, it
Yeah?
appears. Yeah.
All right. So we can go on then. Thank you so much for confirming that. So let us start with the content, and we will go through these 4 main points. And I also would like to remind you that each presentation has a page in the bottom of every slide. So we can refer to it if you have any questions about it, and you can just mention the page. And I know that statistics can be a bit dry, but we will try to make it a bit more interesting with the study example. So you will get some illustration about the application of the statistic test. So before we go to the overview of some basic statistic tests, it is important for us to understand the term used in statistic analysis. We start with the measures of variation. Here, the range is the simplest measures defined by the difference between the largest and smallest value of your observations. However, we need to acknowledge that the range gives us no idea about how the other observation value lies between the lowest and the highest value. And we also have the interquartile range to give some idea about measures of variation. We have seen this interquartile range in the previous webinar, but we can have a look very quickly about this in the next slide. So here you can see that the interquartile range, like what I mentioned before, is indicate the 50% of your distribution data. And it range between the lower quartile and the upper quartile. So it gives better illustration about your measure variation other than just mention your highest value and the lowest value. But it is not very common for us to report the range or interquartile range as our measures of variation in any statistical report. So normally, the most used in statistical analysis preferred for the measures of variations is the variance and standard deviations. Variance itself is measures of the square of the unit of the observations, while standard deviation is more convenient to express variations in your observation because it expressed in the original units by taking the root square of the variance. To give you some illustration about this, for example, if our observations of the interest are in kilograms, for example, we want to assess the birth weight, so the variance is in kilograms square. This it will be more convenient for us to interpret the variation in standard deviations because it will be in kilograms, not kilograms square. So it gives us more convenient way to see the variations because it is expressed in original unit for the standard deviation. Next, we want to discuss about standard standard error. It is I think it is quite common that students sometimes confuse what is the difference between standard deviation and standard error, and which one we need to report in our statistic report in your thesis or in your any academic report, any other's academic report. So I will explain about this shortly. First, we want to agree that samples are useful to make inference about our study population. And the sample is unlikely to be exactly equal to the population mean. Thus, there is a different sample. Thus, a different sample may give us different estimations of the population mean. This is due to sampling variation. As an illustration, imagine that we want to collect several independent samples of the same size from the same population. For example, we sample 5 participants of this webinar age and calculate their mean age. If we do the random sample 10 times with the same sample size of 5 participants in each sampling, it will give us different sample chances it will give us different sample mean age. So that's we call a frequency distributions of these means called sampling distributions. The standard deviation, like the one that we see in the previous slide, the standard deviation of sampling distribution is used to wait a second. Used to explain standard error as well. So the standard deviation measures the amount of variability in the population, and standard error will give you indication the amount of variability in the sample mean, and it gives indication how close the population mean is likely to estimate by the sample means. As you can see here, if you look at the formula of standard error is equal to standard deviation divided by square root of your sample size. This also means that if you have larger sample size, the smaller your standard error will be. And this also means that the shorter your confidence intervals, that means also that the better result of your statistical inference result. We will talk about the use of standard error in confidence interval in the next slide. So here we talk about confidence interval. So the confidence interval itself is a range of values that we can be certain contains the true means of the population. And it expressed by the range of numbers. And I also want to highlight the difference between confidence interval and confidence level. This one is just like standard deviation and standard error. Students often confuse about confidence interval and confidence level. So if the confidence interval expressed in a range of number, confidence level is expressed as percentage. We normally use the 95% confidence level, but at least we need to have 90% confidence level for our study to be reported or to be published in a journal. It will be better if you have 99% confidence interval, although it's not very common. The common one to be used for the confidence level is normally 95%. The confidence level means that if we repeat our survey over and over again, 95% of the time we will get result. We will get result that match with your population. We will have a look the formula of calculating confidence interval. Here, we can see that the confidence interval has a relation with the confidence level that you choose will affect to your calculation of the confidence interval, and also it has relation with the standard error. The range of confidence interval represent as your lower limit and your upper limit. If you can see here, 90% of confidence level here is 90% confidence interval here. We related with the 1.64 as the Z value of statistic. So this one is correspond to your choice of confidence level. So if you choose 90% as your confidence level, so this is the formula you need to calculate your confidence interval. But this one is more common, the 95% confidence interval. So if you choose 95% confidence level, that means you need to choose this formula to calculate your range of confidence interval. And this one for the 99% confidence interval. If you want to look at the confidence interval as illustration, now I would like you to focus with the A. This is the range of confidence interval represents by the 95% confidence interval. In here, based on this figure A minus A to A, we are certain that 95% of our confidence interval mean range will contain the true mean of the population. But don't forget, here we also accept there is 5% probability that our confidence interval does not include the population means. And if you look at the B, here, the minus B to the B, here we can say that we are certain that 99% of our confidence interval range will contain the true means of the population. And also here, we need to accept that there is a possibility that there is 1% probability that our confidence interval will not include the true population mean. So statistic is not things that very exact. We present things by percentage, and we also accept that there is a probability that our result did not represent the true mean in the population. So now we can step forward to the hypothesis and significant tests. And I would like you to think a moment about the various research questions. You can see that you can try to read the various questions here, which we will use as our study example. I will ask you to take a moment to read this for 2 minutes and see what you think about it. Okay, yeah. How was it? Sounds like familiar kind of research questions. Perhaps it's quite similar questions that you have right now for your research study. Now we will learn how to analyze this kind of research questions through the significant tests in the next slide. So the hypothesis or significant test is measures strength of evidence linked to the statement about population parameter. So significance test is normally reported in briefly by the numerical summary, what we call with p-value. We will talk about p-value in the next slide. Before we talk to the p-value, I would like to give you some terminology about hypothesis. So the hypothesis is divided into null hypothesis and alternative hypothesis. The null hypothesis means there is no effect. Does this mean that the groups being compared are exactly equivalent? While the alternative hypothesis corresponds to the evidence of difference in between groups of the predictor variables. So the significant task means we want to search evidence whether we need to reject the null hypothesis and accept the alternative hypothesis, or our result can also be we need to accept that there is no difference. That means we need to accept our null hypothesis. That means there is no significant difference between your groups. It can be like that. And we need to decide how small is p-value should be before we know that we reject the null hypothesis. The larger the task statistic result correspond to the smaller of your p-value. P-value less than 0.05 implies to the evidence of statistically significant result to justify rejections of the null hypothesis. And p-value 0.05 and above implies that you cannot reject the null hypothesis because there is no evidence, significant evidence that there is any differences between your groups. In the statistical report, it is very important for us to report not only p-value, but also your mean and your confidence interval, the range of your confidence interval. So before we move to which statistical task that I can use to analyze my statistic data, I would like you to try to remember about assessing normal distribution. If you are just follow the part 2 of the webinar, do not worry. I will do a brief review about this in the next slide. So in the previous webinar, we assessing our normal distribution based on these key points. The normal distribution is not only important because we want to decide which statistical task that we want to use, but also it is a good empirical descriptions of your distribution of your variables. And assessing the normal distributions is your first step. So it is essential before you perform any statistical task. You need to perform the normal distribution first. You need to know whether you have normal distributions or non-normal distributions, because it will relate to your choice of statistic tasks, whether you're going to perform parametric tasks or non-parametric statistical tasks. If you do have a normal distribution, you can assess your data based on the parametric test. But if you don't have normal distributions, there is several things that we can do. First, we can transform your data and see whether it will follow the normal distribution. I will explain about this in a later slide. And if after you do transformation, you still find it your distribution non-normal, it is all right. You can go with the non-parametric statistical test as well. Also, I would like to remind you that we only need to do normal distribution assumptions if your outcome of the interest is in continuous variables. If your outcome of the interest in categorical variables, there is no need for us to do normal distributions. Assumptions or normal distribution check through these key points I mentioned before. So basically what you produce from your normal distribution, the most important things is the histograms. You want to see your frequency distribution, your shape of frequency. And these figures give you some illustrations. The A is the symmetrical shape. It's very ideal here, and it's also known as a bell shape. The bell is tall and narrow for small standard deviation, and it could be also short and wide for large standard deviation. And in normal distribution, mean and your median will be relatively similar number. And if you see the figure B, this one is positively skewed, you can see that the mean normally is on the right peak and the long tail is in the positive directions of the line. And if you see the negatively skewed in figure C, you can see that the mean will be in the left of the peak and the long tail is in negative directions like this one. To give you more clear illustration about this, I give you some example from my previous work. You can see that here it's obviously this one is positively skewed, and you can produce these histograms using a statistical software. SPSS, Stata will give you this. So you can see some illustrations straight away whether you have a normal distribution or skewed distributions. Besides histograms, we can also examine our data distribution through box and whisker plot. This is what we call box and whisker plot. And in this example, we can see a positively skewed distributions because you can see that there's a long dot here correspond to the positively skewed distribution. And the dot here actually indicate our outliers, which mean that the observation data are lying well beyond the range of the majority of the data. So beside histograms and the box, we can also see it by the QQ plots, whether we have normal distributions or skewed distributions. If you do have a normal distribution, normally your data will be close to the diagonal line like this one. And if you see the second figure here, this is correspond to the skewed distributions, as you can see here. Is many of this data is not in line with the diagonal. The next one, beside histograms and the box plot and QQ plot, we can also assess the absolute skew value and absolute kurtosis value. Again, you can produce this skew value and kurtosis value through the statistical software, such as SPSS and Stata. The reference of substantial departure from normality for the absolute skew value is larger than 2.1. If you have skew value larger than 2.1, it gives you some indications that you have a skewed distributions. And for the absolute kurtosis value, if you have a value proper larger than 7, that may be used as reference that you have departure from normal distributions. That means you do have a skewed distributions. To finally arrive in the conclusion whether you have normal or skewed distribution, you need to search evidence. So it's a cumulative evidence of normal distribution assumptions, which we have discussed in the previous slide. So it will involve the examination of your histograms, box and whisker plot, your QQ plot, and also your absolute skew value and absolute kurtosis value. And this assessment of normality of the distributions is essential step before you can perform any parametrics on or non-parametric tasks. Now we go to the sum of the basic parametric tasks. It is safe to say that perhaps most of people are more familiar with parametric tasks rather than with non-parametric tasks. The non-parametric itself normally called as distribution-free tasks because we don't need assumptions about normality. If we have, if our data is quite ideal and it's followed with normal distribution data, of course we can do the parametric tasks. Here we want to do a comparison between two means. So if you want to do comparison between two means, you can either do independent t-test and the paired sample t-test, depending on your on your objectives and also depending on your data. In the t-test, our outcome variables, our dependent variable should measure in continuous scale. So you need to have continuous data here. For example, the birth weight that we mentioned before. And for the risk factors or predictor variables, it should consist of two groups in your categorical variables. Examples of the independent variables can be, for example, gender, and you can divide it into two, male and female. And it could be also employment status, like employed and unemployed, or it can be also, for example, the smoker groups, and you divide it into two groups, the active smoker groups and the non-active smoker groups. That's just examples of the risk factors that fall into categorical variables. And it also needs independence of observations. What we mean by the independence of observations means that there is no relationship between the observation in each groups or between the group themselves. For example, there must be different participants in each group with no participant being in more than one group. That's mean for example, I illustrate the examples with smoker groups and non-smoker groups that's reflect to the independence of observations, because the one in the smoker groups mean they do smoke and the one in non-smoker groups means they do not smoke. And surely the important things is your dependent data should follow the normal distributions. And what about if you want to assess before and after treatment of the same participants? That is means you comparing two means as well, but you cannot do independent t-test in that case. You have to do pair sample t-test, because here the assumption is almost quite the same, but the dependent variable should be measured in a continuous scale. But the differences is your independent variables. Your independent variables, if you do pair sample t-test, your groups is related groups. That's mean, for example, you assess people before the treatment, and you will assess the same group of people after the treatment, and you would like to compare whether the treatment makes any effect. So we will go to some examples of the independent t-test. For example, we take the questions that we present in the previous slide. Is there any difference between man and woman in mean systolic blood pressure? Here we need to go from null hypothesis. So in the null hypothesis, we assume that there is no difference in mean systolic blood pressures between man and woman. And after we know our null hypothesis, we need to define our independent and dependent variables. Your risk factors, independent variables, is categorical variable is man and woman, and your dependent variables is the systolic blood pressures. After that, you need to perform the t-test. This is the formula of the t-test. So the test statistic for the t-test is the differences in means divided by the standard errors of the difference in means. And then based on this data, we can correspond to our p-value and whether we will get any evidence to reject the null p-value, which means there is difference between man and woman groups, and the p-value should be less than 0.05. If our p-value is larger than 0.05, that means we don't have any evidence to reject the null hypothesis. That means there is no difference between man and woman group in terms of their systolic blood pressure. So now we go to the pair sample t-test. The question is there any significant change of the oral hygiene index? This one is the simplified oral hygiene index score before and after periodontal treatments. As usual, we need to start with our null hypothesis. The null hypothesis can state that there is no difference in means between your oral hygiene score before and after periodontal treatment. And our statistical task will search evidence to whether we need to reject the null hypothesis or we need to accept it. Here, our independent variable is a set of participants, and each participant should be examined 2 times in a before and after periodontal treatment. So before the periodontal treatment, we examine their oral hygiene status, and then after periodontal treatment, we examine the same participants about their oral hygiene status, and we would like to see whether there is any improvement. And our dependent variables is the oral hygiene score before and then after treatment. Here we do a pair t-test, and then we search some evidence whether the periodontal treatments such as scaling or root planing may improve participants' oral hygienes. Again, we have to highlight that we need to have normal distributions of the oral hygiene score before we can perform the pair sample t-test. So what about if we don't have normal distributions and we want to compare the 2 means? Here we would like to discuss about the equivalence of the t-test and also equivalence of the pair t-test in the non-parametric test. The non-parametric test means we are relaxing our model of normality distributions. So the assumptions, if you see that the assumptions of the Mann-Whitney test and Wilcoxon test is quite similar to the one that we discussed about t-test and pure t-test, except here we allow to have non-normal distribution data. For the Mann-Whitney test is equivalent to the independent t-test, and the Wilcoxon test will equivalent to the paired t-test. So it's not the end of the world if you don't have any normal distribution. You can still analyze your data through the non-parametric test as well. And it is acceptable as long as you mention it about your distributions, and you need to present evidence of your normality distribution based on the key points that we talked before about the histograms in your box plot and your TQ plot and the absolute skew value. What about if you have predictors that contain more than 2 groups? And here you can do one-way analysis ANOVA, and it is used to determine whether there are any statistical significant differences between the means of 2 or more independent groups. And previously in the t-test, we can only allow to have predicted variables which have 2 groups of your categorical variables. But in ANOVA, you can have 3 groups or 4 groups as your predictor variables. Other assumptions is quite similar with the t-test and then pair t-test. It is quite similar. The one-way analysis of variance is correspond to the t-test, but here we are allowed to have more than 2 groups. And then one-way repeated measure ANOVA is equivalent to the pair t-test, but here again we allow to have more than 2 groups. We will go through studies examples, which we can do the analysis with the analysis of variance or ANOVA to measure the significant tests. Here we have 3 groups in our independent variables based on their age groups. Here we can see that we do have 3 different age groups here, to 20 to 30, 31 to 40, and above 40 groups. And we want to assess their systolic blood pressures. We can do it with the one-way analysis ANOVA, and we will search evidence whether the p-value is less than 0.05. Also, I would like you to highlight that the ANOVA, the one-way analysis variance, is an omnibus test statistic, and it cannot tell you which specific groups were statistically significant different from each other. For example, you have 4 groups. It cannot tell you that the statistical difference is in your first group compared to the 4th groups, or your or it can be your second group if there is no significant difference between your second groups and your third groups of your categorical variables. So if you want to know about determining of which of these groups differ from each others, so you can do a post hoc test. This will be it more advanced statistic, but we will not go for it and due to time limitation of this webinar. Here we want to know that we want to assess the oral hygiene, for example, after the periodontal treatment, but we want to assess in more than 2 groups. In here, for example, we want to assess their oral hygiene a week after a full periodontal treatment, or and then months after periodontal treatment and then 6 months after periodontal treatment, because normally the periodontal treatment can need sometimes to give some clearly evac on your periodontal tissue, for example. Here we use one-way repeated ANOVA, because in the independent variable, we do have a set of the same participants, but we assess this each persons of the participants will go through examination 3 times here. And then the dependent variable is the oral hygiene score. And we will calculate the t-test. I'm sorry, we calculate the one-way repeated ANOVA here and search evidence of our p-value. So what about we don't have normal distributions and we want to assess mean from several groups? Is there any way that we can do? So this is the answer of that. So you can do non-parametric tests. And non-parametric test is correspond to the non-normal distribution dependent data. And we can do Kruskal-Wallis test or Friedman's ANOVA for assessing the comparisons of means from several groups. Here, the assumptions is quite the same, like one-way ANOVA and one-way repeated measures of ANOVA, except here we accept that we don't have normally distributed data. The Kruskal-Wallis test is equivalent to the one-way analysis of variance, and then the Friedman's ANOVA is equivalent to the one-way repeated measures ANOVA. As I promised in the previous webinar, we will do a brief discussions about the choice of transformations of the non-normal distribution data. So when you do have a non-normal distribution data, the choice is not going straight forward to the non-parametric test, because it's very common that whether we should just straight away choose non-parametric tests if we do have non-normal distributions. I would like to say no to that, because then we can do some effort of the data transformations to see whether we will obtain normal distribution data after the transformations. Here is some choice of transformation that we can do depending on the shape of your distributions, whether it is positively skewed or it can be negatively skewed. If you have positively skewed distribution, the first thing you can do log normal. So you transform each of your observations into logarithmics with this formula here. So your observations, and you transform it into logs of your observations data. What about if you have really positively skewed data and the log normal is cannot transform your data? There is another options you can do. It is the reciprocal transformations. The reciprocal transformation is stronger than the logarithmic, while the square root transformation is weaker than log normal. So if you have a very positively skewed data, first you want to transform your data with log normal, but when it is not still give you non-normal distribution, you can try the reciprocal transformations and see whether it will follow the normal distribution data. And for the negatively skewness, we cannot do the log normal to transform our data. We need to do square or cubic transformations. And the strength of the transformation is correspond to the increasing order of the power. Here, we already talk about the comparison between two means or several means, and the comparison of two means and several means in a parametric task and a non-parametric task. What about our outcome is not in continuous data? What about our outcome is in categorical variables? That means we need to do a task to compare the difference between two proportions. And here, you don't need to perform any normality. You don't need to assess normality distribution of your data, because your data, your dependent data, is not in continuous variable rather than in categorical variables. The task to measure these associations is called chi-square test for independence, and it is used to discover if there is any relationship between two categorical variables. That means your dependent variables, your outcome of variable, is in categorical data, and your risk factors or your independent variables is in categorical data as well. So you don't have any continuous data here. And the lowest expected frequency in each group of your categorical variable of your predictor should be 5 or more to do the chi-square test for independence. For examples, you have you measures data about man and woman, but you only have 4 people in man category and 200 participants female. You cannot perform your task of association with chi-square test. You need to do Fisher exact test for this. Perhaps if there is any more times in the future, we can talk about this. But yeah, due to time limitation, we'll just stick to the chi-square test. And I think it's very rarely as well. You have a very different number size of participants in your groups. Like I mentioned before, is 4 and 200 is very different. That means your data is not really, perhaps it's not really correspond to the true populations. But there is chance that you can get that kind of data. Here, for examples, we have a questions whether there is any association between gender and smoking behavior. Gender is categorical variables, and we want to know our smoking behavior to the categorical variables as well. So here you don't define your null hypothesis, but you start with your research questions. For example, here, is there any association between gender and smoking behavior? And also you can have another phrase of these questions. For example, you can see whether are males more likely to be smoker than females? Or you can also have questions like, is the proportions of males that smokes are the same as the proportions of females that smoke? And again, here I mentioned it that we will have categorical variable as our independent variables or risk factors, and we will have categorical variable as well as our dependent variables. Here, the independent variable is gender, gender is unordered categorical variable. So it's divided here into female and male. And then smoking status into yes or no. Although you can also have other categorical variable. You can also have more than two groups of your categorical variables. For example, you have your smoking status can be active smoker, non-smoker, and can be previous smoker, the one that smoked in the past time, but they already stopped at the present times. You can also have that kind of dependent variables. And then you can perform the chi-square test and see whether your p-value will be correspond to the less than 0.05. That's mean here, if you do have less than 0.05, that's mean there is evidence, significant evidence that there is differences between the proportions of male who smoke and compared to the proportions of female who smoke. What we have learned today is are mostly basic statistical tasks, and of course there are more advanced statistic tasks which we couldn't cover today due to time limitation. So there are other things like logistical regressions, linear regressions, and many more. But I hope after today's webinar, all of you will have a better understanding about some basic statistical concept, and hopefully our webinar will help your future research and study. This is a glance of more information about Edinburgh Dental Institute, the University of Edinburgh, and if you're interested to, you can access this through the website here. And we have undergraduate, postgraduate, and online programs within the Dental Institute, and you can have a look at this website if you are interested in about pursuing further education, perhaps in dentistry, or you can also see other faculty, for example. As in our webinar, I would like to present you another beautiful pictures of Edinburgh, which I took by myself during some of my weekend walk through the city before the COVID-19. But yes, you can see the pictures of Edinburgh in summer. I think it's so beautiful, and it might give you some reason to visit the city and perhaps pursuing further education in the city. And all right. Is done now, and I'm happy to take any questions from all of you. Thank you so much. Thank you.
Thank you so much, Dr. Marisa Hezriana, for this great presentation that we have. Now, before I forget, I would like to inform the participants to fill in their prospectus. It is provided in the YouTube as well as in the website of Fakultas Kedokteran Gigi Unpad, and it will be closed at 9 p.m. Jakarta time and 3 p.m. UK time. Okay, now we go to the discussion session. We already have 2 questions from the audience. First is from Carolina Stephanie. Good afternoon, my name is Caroline. If I may ask, is the number of sample affect the normal distribution? And is there a standard percentage or number of taking samples in order to get normal distribution?
Okay.
Please, Stephanie. Yeah.
All right. Thank you so much for the questions. Actually, it's that's the questions that you need to ask yourself before you conducting any quantitative data collections. So it is very important, and thank you for excellent questions. So I would like to go here. So if you have a very small sample, chances are you will have non-normal distribution data. That's very common if you have a small number of participants, you will have non-normal distribution data. Because the reason why it is very common to have non-normal distribution data if your sample size are small, because this kind of study can be really affected by extreme value. If, for example, you only have 10 participants in your data collections and you want to assess their age, if you have 9 people who have age range between 20 and 30, but one participant's age is 100, for example, that means there is a possibility you will get a skewed distributions. So it is very important for you to calculate your data and to choose your confidence level in your sample size calculations. So if you want to get a good sample size before performing your data collections, you need to think whether you're going to calculate the 90%, 95%, or 99%. Ideally, you will choose the confidence level 95%. But if it is 90%, it also acceptable. By thinking about this in the beginning of your research, you will get a proper estimations of your sample size. Here you can see that if you do calculations with the 90%, wait a second, I will just go, yeah. If you can see here, the standard error correspond to the standard deviation divided by n sample size. So it is indicated the larger your sample size, it will give you a better standard error. So it will give you a better, you will get smaller standard error. That means also there is a chance that you will produce you will produce a better sample size calculations. So I don't cover the formula of the sample size here. So the sample size can be calculated with the simple sample size calculations, one of the way, and the second one is with the stratified sample calculations. It's really depend on your purpose. For examples, you want to do data collections in 3 different districts. So that 3 different districts may have a different number of population in each districts, and you want to do more proper calculations based on the district population. That means in stratified sample size calculation, for example, you don't do, for example, you would just do, I'm going to do 50 participants in district A and 50 participants in district B and C as well. It might be not proper for your sample size calculation, as it is not correspond to the number of real population living in that district. So you need to go through the stratified sample size calculations. So there are 2 ways to do that, is with a simple sample size calculation and stratified sample size calculations. And you ask whether there is any chance to reduce the chance to get a non-normal distribution is by calculating your sample size correctly in the beginning of your data collections. So you choose your confidence levels, and because the formula of sample size will need you to decide the confidence level that you're going to use for your statistical analysis. And one of the tips is that you calculate at least 2 confidence levels with your sample size. Could be 90% and 95%. So if you normally, if you use a confidence 95%, you will need more participants than the 90% confident interval. So you can see whether you can aim to collect at least your sample size data. Your sample size data will have at least confidence level 90%, and if you can get more participants and follow the confidence level 95%, it would be better. So yeah, I hope it's help for you to do the sample size calculation in the beginning of your research. Thank you.
Okay. Maybe, sorry, maybe the participant or the audience can write the question in the comment box of YouTube. Yes. Now we have the second question. It is from Siki Hakam. Siki Hakam asks about the distribution. What if the distribution is not normal? Can we continue to parametric test if the sample size is large? Any minimum sample size for this condition? And if I have 2 groups of sample and would like to check the difference using independent t-test, but one of the groups is not normally distributed, continue to parametric or non-parametric? Thanks.
Can you put the questions on the screen so I can read it clearly?
You
Please.
can read it in the Zoom group chat, in the chat.
Okay, wait
Okay.
a second, I gotta see.
In the chat, okay? The second question from Zikri Hakam.
Okay, yeah,
Okay.
yeah, sure. What if you have non-normal distributions? Like I mentioned before, before you decided, oh, I have non-normal distribution, perhaps I should just go to the non-parametric test. One of the way is you can try to transform your data based on the choice of transformations I've mentioned before. So if you have a positively skewed data, you can do log transformations or reciprocal transformations. And if you have negatively skewed data, you can also try to transform your data into, for example, into cubic transformations and see whether it will follow normal distributions. If it is do follow the normal distributions after you transform your data, then you can go to parametric tests. One of the way there is a more advanced statistic term, which is called central limit theorems. Basically, the central limit theorem will allow you to do parametric data, even though you have a non-normal distribution, but there is some requirement about this. One, you have to have at least 30 participants in your each groups, and you have to assess your homogeneity of variance. If it is the homogeneity of variance is equals, then you can perform the parametric test without transforming your data. But it is more advanced in statistic, so you need to perform some of other assumptions, for example, the homogeneity of variance. So the next questions, if you have 2 groups of sample, would like to check the difference using independent t-test, but one of the group is not normally distributed. Okay, continue to parametric or non-parametric. Again, these questions basically said if you have 2 groups of sample, for example, man and woman, and then we can see in men's group the distribution is normal, but in the woman group the distribution is non-normal. Here we can follow the transformation choice of one of the way is choice of transformations, and see whether you will have normal distribution. If you have normal distribution after transformation, you can go ahead with the parametrics. And the second one is to employ the central limit theorems. Like I mentioned before, if you have at least 30 participants in each groups, you potentially may do the parametric task. But again, you cannot straightforward doing a parametric task by just employing central limit theorem without checking the assumptions behind the central limit theorems. Yeah, so there are two ways to do transforming the your observations data, and the second one is to employ the central limit theorems. Thank you.
Okay, thank you very much for the answer, Dr. Marisa. Now we have the third question, but it doesn't appear yet in the chat. Let me see. Please wait a moment. Okay. This is from, I think this is from the pediatric resident from dental faculty. My research is about oral hygiene index simplified, pH, and saliva viscosity on autistic children. I use parametric Pt test to see the difference in oral hygiene index simplified score, viscosity, and saliva pH before and after video education. Is that a correct choice of statistical analysis? Thank you, Doc.
Yeah, right. So here, first I would like to know your dependent variables. If, for example, your dependent variable, you divided your autistic children into two groups, and you want to see the before and after video educations, you want to assess their oral hygiene index and their saliva viscosity, for examples, and you want to see before and after, it is a correct test to do. But if you have more than two categories in your dependent variables. For example, if you divided your autistic children into three groups, then you cannot do PRT tests. It's rather than to do that, you can do the repeated measures of ANOVA that I mentioned before. I will go straight to that. Wait a second. Yeah. Here, if you have more than two categories in your dependent variable, for example, you divided your autistic children into three groups or even four groups, you can do one-way repeated measures of ANOVA to analyze your data. But if you only have two groups in your autistic groups, it is a correct statistical task to do pair t-test, pair sample t-test. And again, it's based on the assumptions that you have normal distribution data of your oral hygiene index and your saliva viscosity observations, for example. I hope it's helped. Thank you.
Okay. I think we already have three questions, and maybe we should have the last one. The last one is about the randomized control trial. If there is a dropout or maybe an outliner of the data, can we exclude the data from the statistical analysis? Or if we put the intention to flip, then we have to include the data, not to exclude from the statistical analysis.
Yeah. Thank you so much. So if we have outliers data, one of the way to before we perform the statistical analysis is to check that those outliers data. and we can see whether the outliers data it's a real data or it can be or wrong data. For example, you only have a range of possible score 0 to 10, but this outliers is 20. That means it's not it's completely not possible. So you can treat that outliers as missing value.
Okay.
But if it is a real data, for example, in the age, you will have mostly your participants, for example, in 20 and 40, but there is other participant who is 89. That means it is real data. It is a possible data. So we need to include that into our analysis. And we cannot treat that as missing value. But for examples, we have a category of smoker, like I mentioned before. We category a non-smoker as 0 and active smoker as 1 and the previous smoker as 2. And then in your data, you get 5. You get data that is 5 means that data is not possible because you only have category 0, 1, and 2. So that means you treat that as missing value, and missing value means that you don't put that into your analysis. And in your statistical software, you can do that. You can put some of the outliers into a missing data. So in the analysis, it will take account that you do have missing data. Thank you.
Okay, thank you very much, Dr. Mariza. And I think the time is out, yeah? Yeah, unfortunately, because the limitation of the time. But then we come to the end of this webinar. Dr. Mariza Hidriana, we are very grateful with your kind willingness to share your valuable knowledge. And I hope that we will continue the collaboration in the near future.
Thank you so much. Thank you
yeah.
I'm really happy to share.
Yeah, thank you so much. Stay safe and healthy, everyone. So take a big applause for Dr. Mariza.
Thank you so much, everyone. Have a nice day.
Yeah, have a nice day to you all. Bye-bye.